working, it got set and gave an error. So I don't know. Let's see. Well, oh, that's okay. Wait a minute. No, no, no. That's what is going on. It says it's there, but I can't find it. Give me a second here. Or here, let me look on the web itself. Let's see. Golly. Okay. Okay, it says it's there. Okay. I'm just going to take it as though it's there. And we'll just go with it. So let's see. Um, oh, they took away. Okay, so equipment changes in here each day. It's hard to keep up. Sometimes it's not possible. Let's see. This one, this one. Okay. That one, that one, that one. Wait. That one? Okay, so let's see. Let me find the edges of the thing. I don't. Okay. So at least, okay, looks like I have all this all the way maybe to there, maybe? I don't know. Oh, further. So I get a larger spot this time. Okay. So we talked last time about, oh no. I may be going down the hall looking for markers. Um, we talked last time about this, and then having UR and U theta, and we found that UR is a function of time and U theta was a function of time because they kept moving. And so I'm going to try to get all the way from here into a problem. So what we also found last time was this U theta, and the change of U theta with respect to time was equal to minus UR. Then we also, as a side note, we kind of realized that the change in the I vector was nothing. It never changed. And the change in the J vector was nothing. Actually, there's not one here, but the change in the K vector is nothing. These are all fixed, so they don't ever change, which is kind of convenient. That's how we use this. That's how we use that in order to get our way to this. In other words, we basically had UR is equal cosine of theta I plus cosine of theta j, and we found u theta to be minus sine theta I, cosine theta j. So we found that. We took its derivative. We found out if we took this one's derivative with respect to time, we ended up over here, and so on and so forth. If you don't mind, give me a second, and I'll log in Blackboard and then turn on the screen so I can show you where this is in the thing. Did I have it up? I had the, okay, let me go into Blackboard. So at least you'll have a context of where this is. And I actually may have forgot a term, but let me get to that in a second. And the term is the theta dot, so hang on. Whoa, whoa, whoa. I have so many passwords. I can't keep up with them. And so, well, as this is coming up, let me go see if I can correct this one thing that I had. And hang on, this is dynamics. And then I go to content, and then I go to the Pearson text. That'll take a minute to come up. Okay, so last time I just noticed I forgot something. Okay, so let me fill it in. Okay, so if I were to take this and do this, what have I forgotten? Okay, what I forgot was this. Okay, so this means theta dot dur d theta. That part was the part, so this should have been written like so. And if I want to know the rate of change, then what you'll find out is dur d time is equal to theta dot times u theta and dur. And we'll put this together in a second. And let me reference now. I can drop the screen and then move it back up. Uh-oh. Timestamp invalid. Oh no. Okay. Let me try it again. Theta dot, okay, theta dot is, look at that, it wants me to buy the book, even though, okay. Buy now, need to purchase the, okay, let's see, can I even enter? Oh my God. Okay, all the other stuff is there, but apparently I can't get to the book. Oh God. Theta dot is the, think of it as being, think of it as like this. Okay, so here's my X and here's my Y. And I paint a spot on this wheel and it spins. Somebody turns on the wheel and it spins. Say it's spinning, let's just make this up, spinning at 1,000 RPMs, revolutions per minute, or RPM. Kind of low, so maybe let's add another digit, 1,000. Well, if I have 2 pi radians per revolution, and I have 1 minute equals to 60 seconds, then I have a theta dot of so many radians per second, which is 1,000 times 2 pi over 60. So you can, what you see on your tachometer, you just multiply times 2 pi and 60 and you get that in radians per second. The reason RPM doesn't really work is because for the mathematics is because the units aren't quite right. So it's basically the spin rate of whatever that object is. Now the thing is this is a situation where a few seconds later it's like this, and then it's like this. So you notice here the R doesn't change. For mechanical engineers, that's pretty common. And I'll show you how this breaks down later to a really nice set of equations, because then you can make say you have let me do kind of like this. Say you have, and you've seen this, some of you may have even, so this is a terrible drawing of an engine in which this thing is going like 1,000 RPMs, RPM, and it has its own theta dot, and because of that, because it's spinning like that, looking like this thing goes back. But you already know that your engine, your pistons are going to basically go like, well, if I did this through time and say pick that spot, it's basically going to do this. So my engine piston's just going to go back and forth. And so because of that, that's going to drive this. And that's the theta dot. Does that make sense? So theta dot, okay, and this is something I've noticed too. Change in rate of theta with respect to time is in fact theta dot. I mean, it's the same thing. You know how back a while you in calculus you had this, and what they did is they used a prime to make it so that they didn't have to write so much, is all they're doing. Well, if it's respect to time, it's special, and being special means you don't get the prime, you get a dot, and that's all it is. So the theta dot is basically that. And what I'll do is I'll turn this into a mechanism in a second. And so apparently I cannot, they want me to buy the book, Pearson eText. So, oh boy, geez. Okay, so I can't bring up the book, so. Okay, so what I forgot in the last lecture is I forgot that's with respect to theta. If I want it with respect to time, I have to do this chain rule. Now, how does that get us where we want to go? And so first, before I go on, can I erase this part from here over? Does this part from here over make sense, what I'm saying? Eventually, we're going to get to the point where we're going to do a mechanism, although I don't think we can get there today, but at least I can lay the groundwork. And maybe we could do a little one. So obviously, the whole point of this, everything we're doing is this. Somehow, to get a force inside of a system, I got to get the acceleration. So that's what we're targeting for a while. Eventually, we're going to go for this, because the acceleration isn't what breaks things, force is what breaks things. So to get down to acceleration, I first have to get past and into velocity. So if I have a vector r, which could be listed like this, or could be listed like this. This is listed in polar coordinates. Or cylindrical, depends on the way you look at it. So it sounds weird, and when you're first looking at it, you're like, this doesn't make sense, except that any particle that passes through and does something, so this is the path, you can represent that as a parametric with respect to time and use the ij coordinates, or which is the xy, or you can use the r theta, which would be the ur and the u theta. So now if I'm looking for the velocity, okay, let me just do it like this. Velocity is equal to this, which is equal to, believe it or not, this, which this is a scalar. It's the length or the distance from the coordinate origin, say right here, to that point. So when you get up here, it gets a little longer. Now, if this is the particle path, it's obviously not a constant r. So you had to forgive me for a while, so we're not going to use a constant r until we get to spinning machineries. And so when we have that r varying, we can have the length or the distance from there. So you are plus, now you get something really weird. This is the weird spot. So you get a term here, which is bizarre in the sense that when you did it in here, okay, so if you're in Cartesian coordinates, yes, you'll find him in the book somewhere, and if I could bring up the book, I could find that, where you would find this, dx dt I plus x times di dt plus, because this is a chain rule, and then dy dt j plus y times dj dt. Now, he never really, he only writes this one time in the book, and then it disappears because he says, hey, didn't you know those base vectors don't change with respect to time? So then you get just the velocity in x coordinates is x dot I plus y dot j, which comes straight from there. And by the way, you have acceleration, x double dot, and by the way, double dot just means you take two derivatives of x with respect to time. I mean, you could take put 3 dots or 4 dots or 5 dots, although we don't need them. We don't need those extra dots. And so, yeah, so this is great. However, this is all Cartesian. However, polar coordinates are convenient, and you'll see why hopefully in a minute. So if you turn around and look at this, you'll say, okay, the velocity is equal to. You go back and you just go pluck this thing out right here, and then what you have is r dot ur plus r theta dot u theta. And this is one of the things he writes in the book, is he says, okay, now what we'll do is we'll subdivide that. We'll break it down in a second. So in other words, in polar coordinates, you can have the thing moving closer to or further from the origin, and that's this, and then spinning around the origin. That sounds weird, but you know, spinning around the origin is this one. So let's take a special case. Okay, and the special case is we have a flywheel, or just a wheel, bicycle wheel. I don't know what it is. It's just something that's spinning around. We'll say the theta dot is equal to 100 radians per second. Now, a minute ago, you saw how we could do RPM to that. And say the thing is, most bicycle rims, there's a 26, there's a 20, and stuff like that. But you know what? I want a 24, so I want it 2 foot. Wait, if it's 2 foot, if it's 20, so let's say it's 1 foot radius. So if it's spinning at this rate, and it's 1 foot radius, paint a little dot on the wheel, and how fast is that spinning? Well, what's interesting about it, it's not flying further away from the wheel, and so its velocity is always tangent to its path. Its path is a circle. The tangent to the circle keeps going around and around. And guess what? That's the direction of u theta. And what is that speed? This is the velocity. What he calls it in the book is the velocity, okay, in the theta direction. He calls this in the book velocity in the r direction. So what he does is, I don't think the old book, he didn't write this all in one swoop. He wrote it as v is equal to vr ur times v theta u theta, and vr was this, and v theta is that. So if you want to figure this one out, r theta dot is equal to 1 foot times 100 radians per second, or 100, what's the units of radian actual? It really doesn't have a unit. It's unitless. If you go try to find a unit of a radian, there isn't one. It's a ratio of one length to the other length. So it's just, so somebody called it something because we have to identify it, but actually it doesn't have a unit. So it just becomes 100 feet per second. Now, let's imagine now that instead of this being a bicycle wheel, this is you in a car, and you're going 100 radians per second around and around, and that's this rotational speed. So for just as a case in point, how long does it take you to make one cycle? If you're going 1 radians per second, how long does it take you to come from here, and you're going at constant rate, all the way around back to here? How far did you go in theta? Didn't you go 2 pi? 2 pi radians per, I'll call it, what do you want to call it, cycle? Let's just call it cycle. So you want to go 1 cycle, right? So how long did it take you? Well, what you could do is you could multiply this out, and here, I got to get rid of 2 pi 1 cycle, because I got to cancel that and that. Even though they don't have units, you got to line them up. So it took me 2 pi. Now see, what I end up with is a cycle in 2 pi seconds. So I'd have to flip it over, and I'd say it took me 2 pi seconds to go all the way around and come back. So, you know, I don't want to get too much in this, but if you are asked this question somewhere in all this stuff, just remember that if you're trying to figure this out, you can kind of lay stuff out in units and try to cancel things out to get there. So that's kind of a side issue. But now I want to know, I'm driving in circles. Now, if I'm 1 foot radius, I must be a miniature person. So maybe you put something in there. Maybe you put something there, started spinning around, and you put an accelerometer in there. And you wanted to know what is it going to feel. So to do that, you got to get acceleration. Okay, so you know if you're, and you've done it, we all done it, got in a car and did donuts in a parking lot. You know, as you're going through a corner, say you're going to the left, you feel like you're being thrown to the right. The acceleration is pulling you the other way. So let's try to figure out what that acceleration is. I think I could probably remember 101 foot, but maybe I'll turn it into something like 50 feet and so many miles per hour. So I'll erase this, then I'm going to go through the acceleration, and then I'm going to come up with this thing that you're in your car doing this. Okay, so now to keep going, I have to make it generic in the sense that I can't just assume that this is constant yet. So I'm going to go through the equations without anything being a constant and realize that if I'm doing this, I'm getting the acceleration, which is what I want. So the chain rule, what I'm going to do is that instead of writing things like this, if I've got something and it's a time, I'm going to basically put a dot over it, and that's me being lazy up here. So I do the chain rule, r double dot ur plus derivative of this one times that one plus the derivative of that one, that one times the derivative of that one, which is r dot ur dot. So this gave these. This one has 3 terms, so it's going to give me 3 of them. It's going to give me r dot theta dot u theta plus r theta double dot u theta, and I wrote UR, sorry about that. And then the last one, R theta dot U theta dot. The oddballs are these two. If UR and U theta didn't vary with respect to time, I wouldn't have to worry about it. But I've already established that this relationship looks like this. So now I can just write all this down. Now the nice feature here, let me write it down. And the nice feature is that, so I look back over here, you get R dot, theta dot, because I copied it from here. And then I got to copy the U theta. So what I did, this came to that because of these funny relationships. Now, in the last lecture, you'll see I did forget something. So now I corrected it. And then I was going to bring up the book and show you where it was. And I can't get the book up. It wants me to rebuy the book. So it's good that this is streaming YouTube. I doubt Pearson will look at my lecture and correct my problem. But it doesn't really matter. I still got to do something. So the other one I'm just copying down. And then the last one is the U theta, and it has a minus sign, so I put that. It has a dot, and that has a dot. And this has a UR. Oh, this should be, you know what? I'm going to write it in 2 blocks so I can, I know that's this came up to that with the minus sign. But if you're okay, I can put them back together as a squared. So that's what I'm going to do. Okay, this is a lot of stuff coming at you. And I'm sorry about that. But so what I'll do now is I'll try to regather terms. One of the things you see is this term is repeated twice. Repeated twice? Yeah, it's there twice. And this is the theta, that's a theta, that's a theta. This is an R, and that's R. So in light of this, I'm going to combine and put the URs first. And so what we'll have is R double dot. And I look way over, way over here, R theta dot squared. And then there's UR plus, and I think he puts a plus because everything goes together. I think in the book he lists this one first, plus 2 R dot, theta dot, and then close it in U theta. So what I'll do is I'll line these up here, and I'll start. So in other words, we started with this. We took a derivative, we got this, and I'm just copying now. And then my handwriting kind of went off there. And then the last term, we got this. R double dot minus R theta dot squared. And don't get too hung up with memorizing what I'm doing, just that the end result is we're going to look at these 3 equations. We're going to observe some things. We're going to calculate some things. And then I'll show you, you actually already knew this, but it was just written differently. Okay, and so if you want to derive it or something, the YouTube video is still there, and you can go look at it. U theta, okay. So again, the reason it caused this awful situation is that the base vectors they don't change in length with respect to time, but they change their direction. And so because of that, you take a derivative and you take a derivative first, you get the velocity, then you take a derivative. And it looks awful. However, it's not that bad. Did I copy it down right? That's always the big problem. Okay, so now let's look at you in your car. So you get out here in the parking lot. I'm not advising you to do this, but say there's a big area over there, and you just want to have fun. What you want to do is you want to go, this time I'll make it 50 feet, and this time you're going 50 miles per hour. I'm going to convert everything because you can read your speedometer. So let's say you had some kind of car that was good enough to do all that. What, how much is your acceleration out to the right? Now, this time you already know, okay, so let's say your speed is equal to a constant. So if I were to write the velocity, I'd look up here and I'd say, I'm not changing my R. R is always 50 feet. So R is equal to 50 feet. R dot is equal to nothing. R double dot is equal to nothing. It doesn't change. So now if I look back up here, okay, well first, let's do it this way. So I'm going to write my velocity down. I get 0 UR, meaning I'm not going this way or this way around this circular path. And then I'm going a certain speed in the theta. Now, this is not to scale, but U theta is this way, UR is that way. So it's 50 miles per hour, but I need to convert that 5,280 feet in a mile. I misspelled that kind of, and 30, and then you got an hour, and then you got 3,600 seconds. And then that's U theta. So this is you going 50 miles an hour, which is the equivalent of, if I can operate my phone sufficiently well. Oh shoot, already 5280. 73, about 73.33 feet per second U theta. But what's your acceleration? Now, if you were working this problem before, what you would do is you'd say V squared over R. V being, well, I'll put the numbers in, but we'll look back at that in a second. That looks funny looking, R. So, V squared over R. That's 50, but it's got to be in the right unit, so it's got to be 73.33 squared over 50. I'm not going to calculate that, but I'm going to write this down and look at it for a minute. But you already realized this. Okay, I shouldn't have put a box right there because I messed up I should have just copied it, and I can't hit the back button. So here, in other words, R theta dot U theta. So R is 50, so therefore you would have to say theta dot would equal 73.33 over 50. So you could calculate that and you'll get a number that's a little bit bigger than 1. But let's just hold on to that thought and don't get too hung up with that. Get hung up in this fact. Let's just hang on to that for a second. Now, what is this? This is equal to the acceleration that you're going to feel. Now, bear with me for a second, and let's take a look at this restriction applied to the acceleration. So in this particular case, that's going to be 0. That one's going to be 0. And guess what? You're going to be going a constant speed. Okay, so if you're going at constant speed, what is that? If you're going 73 feet per second, and it stays 73 feet per second, and this is 50 and it stays 50, throughout time, that's going to be gone. Now what is that? That's basically you going a certain speed in a circle and then speeding up. So as you speed up, that increases. You know, that might be 1 radian per second squared, 1 radian per second squared, meaning you're speeding up. Could be minus, meaning you're slowing down. But in this particular case, you in the parking lot, it's nothing. So that means that's gone. Now, let's look at this for a minute. This term right here, it says it's 0. The acceleration, okay, any particular spot, you've got two, let's just say your car is right here. Here's UR, here's U theta. If you were speeding up, then your velocity would be increasing. If your velocity was increasing, the theta would be a number besides 0, and you would just multiply that times r, and it wouldn't be 0 anymore. Meaning, you speeding up over time means that that's equal to a positive number, means that that's equal to a positive number, and r just doesn't change, it's 50. Means that you get something besides 0, and that is going in that direction, tangent to your curve. But you're not. But you still feel acceleration. What do you feel? You actually, the only term that's not 0 now is that one. It's the only non-zero. And what is that one? It says it's in the negative direction, meaning if your car's right here, it goes, the acceleration's going this way. And what is its value? It's r times theta dot squared. But we've already determined that that is your velocity and this is your r, because the velocity in the theta direction is r times theta dot. Theta dot then is v over that, right? Which means you can take this, stick it in here, and I would have r times v over r squared. One of these squares knocks the other out, and you get back v squared over r. So in fact, this is no different than that. The difference here is this one can allow you to speed up. It can allow you to slow down. It can allow you to, as you're going in circle, to wiggle your car and do like this. That one will not be picked up with this. You can take this path and use this to find your acceleration through time. This one is completely general. Always works, no matter how you drive your car. So does this kind of make sense? And if it does, oh crap, I don't have time to do a problem. So here's the problem I was going to do, and I'll kind of lay it out, and then we'll do it next time, because it'll probably show up somehow. I was going to take, the reason you want to do things this way is there's a lot of mechanisms that are built that spin around an axis. And why? Because we can take a driver motor and make it go. If we want to go linear motion, we have to do something to spin it to make the thing go. So let's say you had a rod that was in here and it had some sort of theta as a function of time. And out here there was a collar. I'm not a great drawer. And through this became a path. And your job is to make sure something doesn't break right here. So you've got to find the acceleration before you find the force. And you have to know the mass of it, but we're not even dealing with the mass or the force yet. We're just dealing with the acceleration. Since, you know, you could put your coordinate system right here, and you could have this. If you had this path, you know, r is equal to 1 plus 2 cosine theta or something, or maybe some other, then you could have this path. Guess what? You could take its derivative with respect to time. Now, you might have something very complicated. Notice the simplicity of what you have to come up with. That's the key. Don't get overwhelmed by the fact that there's lots of equations. Now you focus on one simple task. Observe that you have this, this, and this. And you have this, and this, and that. That's all you have. If you're given this as a function of time or something else, take its derivative again. If you were given this as a function of time, derivative again. And then, what else is in here? 2? Well, you know what 2 is. Everything else is. So most of the time, this problems will be given to you where they state something where you can immediately determine that one, and you might have to take a derivative to get this one. And that's it. And so somebody may ask, well, what's the acceleration at 45 degrees? Well, you just say it's 45 degrees, the theta dot's this, the theta double dot's that. Now you have a path, you take its derivative and another derivative, you start inserting things in here, and you get an equation for each one of these. So although it was overly complex, what I just went through, now it's very simple. Come up with actually 5 things. You really don't see theta in here, do you? You only see theta dot, theta double dot, you see r dot, r double dot. That is all you see. 5 things to figure out, insert in the set of equations, and he may ask you something about them that you have to figure out. But as far as the complexity, it's just this, this, and this. At least I hope now you get, like, actually this is in the going away from the axis, velocity going away from you, and the other is going perpendicular to it. This is the acceleration going away or towards you. Centrifugal is right here. This is nothing more than the v squared over r. That's all that term is. This one is the fact that actually you could be accelerating away from the axis or towards the axis, but that's not covered in the other one. These are 2 that are basically here. You can get your velocity change, you're speeding up your car or whatever, and here you have a little bit of a complex effect. That's all there is to it. There's nothing more to it. So don't get caught up in what I just spent the last hour doing, in that, like, oh God, this is so complicated. Actually, if you just watch that lecture once or twice and you're just like, okay, I get what he's saying, now let me work the problems. Then the thing starts here. With this, you do these, you insert, you're done. It's that simple. So does that kind of make sense? So you don't want to make a problem any harder than it is. So what you want to do is kind of get the concept and then work a few of them, and I'll put several of them on the homeworks so that, you know, you can get practice with that. And then, like, mechanisms. For example, you've seen the movie theater where you see the film advancing. There's a mechanism in there that goes in and grabs the film, comes down, and backs out. And guess what? It's run by a motor, and the mechanism just sits there and does that. It grabs the film has the holes on the side. It'll stick its fingers through there, yank real quick, and back out. And all it is a mechanism. If you look inside, it's just a mechanism with forks. If you go look at some factory lines, bottles making, wine or Coke or something like that, they're a mechanism. There's a Pop-Tart factory in Searcy I went and toured. Same thing. There's these Pop-Tarts coming down, and there's a mechanism, and it just sits there, goes over and over. What's it doing? It's being driven by a motor. It's just sitting there going back and forth. That's kind of all, that's the basis of what we're going to do. Then in the next section, I'll show you that actually there's 2 ways to look at this. There's a v squared over r. Then there's this generic thing. Then, believe it or not, these are in polar coordinates, right? It turns out there's a coordinate independent version of all of this that deals with cross products and dot products. You can get the same thing out of that, and I can show you how to do that. The second one, or not this is the second one. The third one is what you would use to build like a mechanism like that. And then there's, of course, mechanisms. I don't ever teach it because I'm too tired, but, you know, somebody has taught it last few times. If you want to get into, I mean, really, robotics, there's 2 or 3 ways you can look at it. There's robots, or sometimes people say, oh, it's just a thing going around and doing the Vex robot or something. That's fine. Robotics also is mechanisms, driving mechanisms with intelligence. So the mechanism may not be something going around the floor. It may be something like, okay, I see a Pop-Tart coming. I use intelligence to say, okay, there it is, I grab it, you know, and then I throw it in the trash. Or there's one that they have a little gate that says, oh, a bad Pop-Tart, and the thing pops in a just a 55-gallon bucket. And so you look down there, there's like tons of Pop-Tarts in this bucket, and you're like, oh, okay. And I ask them, they go feed them to the hogs and stuff, give them the Pop-Tarts, because people won't buy them, you know. Or they get mad. If they buy them and they're broken, they'll take them back, you know. They don't get mad, I guess. They just don't want them. So, well, maybe they do get mad. I don't know. Anyway, I'm done. I'm tired. Yeah, I'm past time. And I never got the book to come up. Okay, it's trying to come up. Oh, you're kidding. Now the book is coming up. Okay. That's hilarious. Well, you know what? Since the other class hadn't started, just to cap off the end of the lecture, I'll switch to the book. And that way, if you want to go back and look at it, even though there it all is, if I zoom in, what happens? Okay. So there's the v velocity, or the velocity. There's the acceleration, which is written with r squared, or r double dot minus r theta dot squared. Okay. I'm done.